describe how to calculate that. It only knows how to go from one point in time to the next, but not at half intervals. So this is the basic difference between these models. So how are we going to solve this model? Integrate, okay. Do you all remember integration? Who remembers integration? Okay. Who's totally forgotten integration? Okay, so you remember that integration is the inverse of differentiation? So differentiation tells you about, here's x of t, and here's t, and differentiation will tell you about the rate of change at a point. So it's actually the slope of the curve at the point. That's the derivative. Integration tells you about accumulation. So if we integrate from here to here, then it tells you about the accumulated values. And if you remember the concept of integration, you can divide it into a finite sum, where these summation intervals, which are called delta x or h, get smaller and smaller, and you get more and more of them. And then when you add this up, it equals the area under the curve. So Archimedes, for example, wanted to find out how to get the area in a circle. The area in a circle was a big problem, and nobody could really do it. And if you have a look at books that discuss this, you'll see that he took a circle and he divided it into these little bits of area, and he got approximations to actually the number pi by characterizing these little rectangles that he could add up. And as he got more and more, he could fit them more precisely into the square. The thing about a rectangle is that you put it through the curve, and the curve is not straight at that point, it's changing, so it's always an approximation. But these approximations and how to calculate them are the basis of numerical integration. So in numerical integration, you have ways of making these approximations more accurate, and we'll talk about that later. But in integration, you're accumulating things, and it's the opposite of differentiation in the sense that if we go from 0 to t dashed, or t prime, of dx dt, which is a function of t, dt, that's equal to, I integrate the left-hand side, I'm also going to integrate the right-hand side, 0 to t primed of rx dt. The reason why I call it t primed and not t is because t here is a running dummy variable that goes from 0 to t prime. So I just want to distinguish between being on the interval 0 t primed and having some value of t that belongs to that interval. Does everybody know this mathematical sign? It means belongs to that interval. Okay. So now the fundamental theorem of calculus tells you that the integral from 0 to t primed dx dt dt can be written as the integral from x at time 0 to x at time t primed dx. So you can think of it almost like you're cancelling those out, but that's not the way it works exactly, but that's just a helpful mnemonic. But it's called a change of variable. So this is your change of variable formula, and that's equal to the integral of, now we can take r out as, I'm actually going to do something different. I'm going to divide both sides by x. Okay, so before I integrate, I divide both sides by x. So that's a formula that it's legitimate to do that as long as x is greater than 0 or not equal to 0. And the reason why I do it is I get everything on this side as a function of x, and everything on this side does not include x. And the reason for that is that I can integrate here with respect to x, and I've got a function of x, and I can still integrate here with respect to t. And r is a constant. So I can take r out, if you remember your integration. Now, the integral of 1 over x dx, does anybody remember what that is? Okay, so it's a log, natural log. So that's the log of x. And we put the modulus sign there to tell us that you can only do this for x positive because the log of a negative number is not defined to be real. Do you remember that subtlety? Who's stunned by it? Like, I totally forgot about it. Do you all remember that? Great, okay. And so that's the log of x going between the limits, x0, xt primed, and then r, and the integral from 0 to t prime dt is just t prime minus 0. And so this then is, now if x0 is greater than 0, you can show that x of t prime will also be greater than 0, and you can drop that out. So that's the log of x t primed minus the log of x0 is equal to r times t primed. And then this is equal to, if we take, what's the opposite of the log function? The exponential function. So if we exponentiate, e to the log x of t is just x of t dashed. And because subtracting logs is the same as dividing the function when you exponentiate, this is 0, is equal to r times t primed. And so this finally tells us that x at t primed is equal to x0 e to the rt. Sorry, I've got to put e to the rt there. I'm exponentiating the size as well. Everybody follow that, okay? And you can look in the calculus textbook, it's there. This is a very, very key formula, and I can always say that if I've got dx dt is equal to r times x with x at time 0, the specific value, x0, this is called an initial value problem because I specify x0 to be a particular number, then in working in this class and in working in any modeling and any sort of basic mathematics that involves a little bit of calculus, whenever you see this, you immediately think of this, and vice versa. So that's very fundamental, and you should just sort of always remember that. Now you can see that if r is greater than 0, this grows exponentially. And if r is less than 0, e to the minus something that is increasing declines from, so for example, if I wanted to plot e to the minus t, I would start off at t equal to 0, e to the 0 is, so if x is equal to e to the minus t, then I start off at 1, because at t equal to 0, e to the 0 is 1. And then when t is 1, I'm down to a value that's 1 over e, and I asymptotically approach the axis. So you all know that for the exponential function. Okay. So let's now take a look at what I have on the board. Okay, so if we have a look here, I've set up the model. I've reminded you of what the derivative is and how you define it. And this is the relationship between a discrete form of this model and a continuous form of this model. And you can solve it by numerical integration. And in this particular example, which is section 6.1, example 2, we talk about qualitative behavior of this model. And in this example on the board, I've used small r, but here you've got capital R, so you just have to make sure. Well, always, sometimes r may be a, or maybe called c, or some other value. And so there are three different cases. Now, the first case is if r is equal to 0, what happens to the equation? We get dn dt is equal to 0. Put that into words. What's the mathematics saying in English? Yeah, it says the rate of change over time is 0, hence the population will stay constant. But the actual mathematical statement is the rate of change of n over time is 0. And then if you come to this, then so if the rate of change of x over time is 0, then it means this is 0. Then it means x at t dashed is equal to x0 for all t dashed. So it's unchanging. So those two statements are equivalent, the ones made about the model and the ones made about the solution to the model. And in your homework, I ask you to discuss this, and it's either constant or growing or decaying. So when r is less than 0, we often say the numbers are decaying. And when it's positive, we say they're growing. But sometimes people say negative growth. So negative growth and decay are the same in terms of this concept. Now, because biologists suffer from physics envy, why should that be the case? Okay, we can trace it back to Nobel, who said, no, it's not true. There are Nobel Prizes for physics and for physiology and medicine, but not for general biology. But anyway, what biologists sometimes are envious of is the fact that physics is a much more precise science. And so physicists can have models, and they can do experiments, and then they can measure what's going on in the experiment to show whether the model is any good or not. And in this way, we can throw away some models in physics in favor of others. So, for example, Aristotle had a theory of how things move. And his theory was totally and utterly wrong. And yet for 2,000 years, people, or maybe, more or less maybe 1,900 years, people said, okay, we accept Aristotle's theory of how things move. And then Newton came along and changed the theory completely, and we get Newton's laws. Now, why was Aristotle's theory able to persist for 1,900 years? Yeah?
Because humans were not encountered with location sense. They weren't trained by those binary physics.
Right, so they couldn't measure things very precisely. For example, they couldn't measure time very precisely. That's kind of crazy to think about in this day and age. But several hundred years ago, how did you measure that a second had passed? Yeah? Okay, so there were sand clocks and various ways of trying to do this. But it wasn't very consistent, and it couldn't be replicated in different places. And when Galileo went to the top of the Leaning Tower of Pisa and dropped objects, he didn't have cameras where he could measure precisely where something was and put a time to it. So people couldn't do very refined experiments, and they couldn't show how how objects move through space in a very precise way. And these problems could only be solved when we came to be able to measure things. And for example, at the end of the 19th century, people didn't believe in atoms, many people, because you couldn't see them. So there was the atomic theory of matter, and some people said, oh, this is just a convenient way of thinking about it. But in fact, there are no such things as atoms. But of course, today we can actually visualize atoms using very refined and high-frequency electromagnetic fields. So biologists, having this physics envy, also wanted to do experiments. They wanted to do experiments to show that populations grow exponentially in isolation. So Carlson set out to do this in the early part of the 20th century. And he used yeast because it provides an ideal organism for population growth studies. They're easy to culture in a liquid environment, and the number of individuals per unit volume can be counted under a microscope. And so we can even look at a picture like that, and you can count these. So you can get some, preferably undergraduate students like yourself who need money, pay you $5 or $10 an hour. Who would do this for $10 an hour? Okay, yeah, so there you go. And that's what happens. Some students will do it for free because they want to work on their CVs, and they want to get into med school, and so they want to say they're doing all these great things, charitable work, working in labs, and so on. So remember to work on your CV if you want to get into med school. So if you want to get into med school, come volunteer in my lab. And so what you can do is you can have this colony growing, you can perfuse it with a liquid that contains all the nutrients, and hopefully you let these cultures grow and you count them. And this is what Carlson did. And you can see here a bunch of points, the red points. And what I can do is I can fit an exponential function to this. So here's the data. And I can fit an exponential function following this procedure here. So I can say, should we fool Richard? So Richard's actually the development of Nova. Hey, Richard, don't say anything bad. You're talking to my class, but they want to see you. Just show them your face.
But you still want to have a class afterwards?
We're going to talk about Nova soon. Okay, I'll talk to you some other time.
Here, I'm coming up. Hold on.
So Richard's at Oberlin, and if you hate Nova, where are you?
I'm waiting to see if I can get the video. Hold on.
Oh, okay, if you hate Nova, then you can write him nasty letters.
Please don't. Okay, hold on.
Okay, there Richard is. Okay.
Hi.
Okay, we're going to have to cut it short now. Huh? There really is. Can you see?
Wow, it's a huge one.
Okay.
Okay.
Whoa.
Sorry to interrupt.
Okay, goodbye. So this would never have happened in my class 20 years ago. Okay, so that's Richard. Very smart guy. Okay, so we propose a model, and then since C here is the initial value, we have a look at the initial value, and we set that equal to what we start out with in our yeast population, which turns out to be on average 9.6 cells per unit area. And then at time 3, and this may be hours. So in this case, hours are a good measure. Minutes are too fast, not much is happening. Days are far too slow in hours. So after 3 hours, the population's gone from 9.6 to 7.2. So if we take logs, this means that taking the log of this side, dividing by 9.6, we get 3r is equal to the log of this. So r must be approximately 0.53. Yeah?
Just out of curiosity, was the concentration of the solution that sustained the population sort of kept at a certain concentration?
I don't know. You've got to go and read the paper, but I would think it's more than sufficient to grow. In other words, it's not limiting. So these are assumptions about the resources for growth are not limiting. So what is limiting is the physiology of the cell. And the physiology of the cell is about the rate at which it can absorb nutrients, get rid of waste, do all its stuff. And so it's no shortage of nutrients. But what it is going to do is, as the cells crowd each other and they run out of space, they're going to interfere with each other's ability to take up nutrients. And so if you do that, what you get is you'll see that it doesn't quite grow exponentially. But now there's an interesting thing that you can do, and that is, instead of plotting n against time, we can plot the log of n against time. If we plot the log of n against time, you'll see that over here, n of t is equal to n0 e to the rt. Then if we take logs, we get the log of n of t is the log of n0 plus the log of e to the rt, which is just some constant, which is the log of 0 plus r times t. So in other words, the log of n is proportional to time. So if we're plotting the log of the population over time, we get a straight line. And we say, okay, we can fit the straight line, and instead of just fitting this curve by starting here and fitting it to go exactly through this point, we can do what's called regression. How many of you know how to do linear regression? So this is something that you'll learn in a statistics class, is how to fit a line through a set of points. In our calculus textbook, we actually do talk about this, and it's not part of this class because this class is not a class about fitting data. But regression analysis is not part of the class, but you can go to example 7 in section 4.3, where it talks about doing this kind of regression. And regression is based on minimizing the sum of squares through a bunch of points. So what we mean by that is, if I wanted to fit a line through some data, let's say I've got a graph over here, and I've got some data points. And then I can put a line through these points. Huh? I'm just talking about, I'm not saying what the axis is. All I'm talking about is the process of regression. So whatever on this axis, in this case, we're fitting log of n, and whatever on this axis, in this case, we're fitting t. There's some plots where you'll actually call log-log plots, where you take log of n and log of t. This is called a semi-log plot, where you take a log of n and t. Here we expect, on a semi-log plot, that an exponential relationship is going to be a straight line. And you say, okay, how far is the point from the line? So you get a vertical distance. But then we could fit another line. Let's say we fit another line like this. So this line goes exactly through this point, so this distance is 0. But here we have a big distance, another big distance, another even bigger distance. And so we say, if you take these distances to the line, and you square each one, and you take the sum, it's called the sum of squares of the residual distance, then you'll see that here you get a huge number for this line and a small number for this line. So we're trying to find the line where the sum of the squares of all these distances is the smallest. And then we say that's the best regression line through that data. So as I said, this is not about statistics and fitting lines to data, but you do need to know about it if we talk about real data and we're trying to fit a model to real data. Now in this class, what we mainly do is we're trying to build models. And how we get the parameters for our models is the other side of it, and that is the statistical side and the parameter estimation side of it. But we're not going to focus on that. We're going to talk about the equations themselves and their behavior. So how many of you have taken a statistics class? So did you not do regression in that class?
It was very light.
Oh, okay. Is anybody who took a statistics class where they didn't mention the word regression? Okay, so you've heard about it then if you took a statistics class. Good. So now there's some interesting questions. If you've got an exponential model, and here what we say is we've got this exponential model of the yeast population, and if it's a good model and we're happy with it, we can say how long does it take for the yeast population to double its size. Now the thing about an exponential model is that the growth rate per unit time is a constant. So that means it's growing the same proportion, it's changing by the same percent. In this case, it's increasing by 53% in each unit of time. Now it's not quite 53%, it's actually faster because the exponential has this it's an instantaneous rate of change of 0.53 that would translate into a percentage change that's slightly greater than that over each unit of time. So for example, we saw last time that if we've got a rate of doubling in each unit of time, and this is happening continuously, then after 1 unit of time you haven't doubled, but you've actually increased by 2.2. So 1 has gone to 2.7, not to 2. So this is faster than, it's going to be a